Hi, hello, this is Jenny. So today's session is digital electronics. In this digital electronics part, we are going to see about the De Morgan's theorem. Okay, so digital circuits, we are making logical circuits to do our calculation or perform some operations in that unit. So for that circuits, logical circuits, because we should get that answer logically. Okay, for example, if you are moving in the track or if you are walking on the road, we should follow the footpath. We can't enter into that land. Okay, land means other vehicles, they are moving in that land, so we don't cross in that land. Okay, so that's not a logical thing. Okay, the same logical thinking or logical circuits we are going to make in our digital platform. So in this digital platforms already we have seen gates are very important. Okay, so maximum we are using 3 gates and or not, right? Okay, so what are the operations, how we are going to perform in that circuit to do the logical calculations, right? So here you can see the negation. Okay, so negation for not operation. Not operation, another technical word is negation. And normal, we can say conjunction. Okay, so junction means and operation. We are going to connect. For example, you are taking the train. Okay, so this is for your example. You can imagine we are standing on the platform. So in the platform opposite, the train is moving on that particular track. Okay, so how many compartments it tie up with engine? Okay, so just imagine one big engine part is there. So behind the engine, we can connect more than 10 boxes or 12 boxes. We can connect. Okay, so engine is the main. Okay, that means junction. So next we are going to connect other boxes. That is conjunction. Okay, so here we are using AND operation. AND operations means you are going to join. Okay, it's opposite from the AND operation OR. Okay, disjunction means whether it is right or wrong. Okay, you can take A or B. Okay, or you can take this boxes, you can join this box, not that box. Okay, so like this decision making we are going to take in that logical circuits. So for that circuits here, we are using lots of theorems. Okay, theorems in mathematical functional, we can use the theorem. In computer applications also we are using theorem. Okay, so in digital electronics we can use lots of theorems, but basic importantly we are making all the things by using of this De Morgan's theorem. Okay, so De Morgan's theorem is full and full consider the case why we are using this theorem. Okay, so then we will make this theorems as the algorithms in our coding. Okay, so for this circuit, the De Morgan's theorems we are going to apply. So why we are applying this theorems in our circuits means the theorems, it produces the answer. What answer it will produce means it will not produce, for example, taking two apples. For example, for apple one is A, another apple is B. Okay, so I'm going to conjunct, that means connect. So I'm going to connect means I'm going to connect with A with B. Okay, here you can see this example. So this is for your AND. Okay, this is for OR. AND means you are going to connect this part and this part. For example, here they given x and y, we can take A and B. Okay, so A B is joined with A, or here you can take X, Y is joined with B, that is AND operation. Okay, but De Morgan's theorem what says means it says A is false or B is true. Okay, whether A is true or B is false. Okay, you can take any one decision. A is true or B is true. A is false or B is false. Both conditions same, but we can choose any one. We can't join each other. So that decision uh, we can get from this De Morgan's theorems. Okay, so that's the reason we are applying this technology in our digital circuits. Okay, so this is the operation for OR operation. Okay, so this symbol is caret. Okay, and here you can see not operation. Not operations means negation. Okay, so you can choose particular part. Okay, so if you are joining means you should use AND operation. If you are taking any one of the part, you should use the OR operations. You need particularly I want this one, like that real-time examples we use negation operations, that means not operations. Okay, so in this De Morgan's theorem or law, both are same. Okay, so here they are mentioning this expressions. Okay, so for example, if you are putting A, that means if you are putting that multiplication symbol, you are going to change as plus. Okay, this is your operator, operand A and B. Okay, the collection of operand as well as operator is called expression. Okay, so mathematical expressions or logical expressions, how we can say in the technical word in our computer applications, we can call it as collection of operands as well as operators is known as expressions. Okay, not a facial expressions. Here in technical words we can say this expression. For example, here you can see A dot B bar. Okay, you can get that answer. I'm going to change this operator. Where is my operator? Yes, dot means multiplication. Okay, so now I'm going to change this operator. Operand should be same. I'm going to change the operator only. Okay, so A bar plus. So the operator has changed right now. So A bar plus B bar. This is your first expression. Okay, and second thing, if your law A plus B the whole bar. Okay, so they given this plus symbol. Now I am going to convert this one A dot, going to split this. They given AND operation, I am going to split this A bar dot B bar. Okay, so I am going to change the operator, not operands. Okay, so this is the two expressions of De Morgan's laws. Okay, so now how we can prove this statement? Okay, here you can see they given the calculation x dot x plus y dash. The expression is x dash dot y dash, right? So another example they given x dot y the whole dash. What they given? X dash plus y dash, because we are going to change the operator, not operand. Okay, so that is the usage of De Morgan's theorem. Okay, next they given some examples. Here you can see our expression is x plus y whole bar equal to x dash dot y dash. how we are going to prove this statement is expression is true or wrong. Okay, so here you can see the fundamental Boolean laws. I'm going to apply two rules. First rule is complement rule, another one is distributive property. Okay, the complement rule means here you can see a plus a dash equal to 1. Okay, whether a dot a dash, you get the value 0. If it is plus, the operator is plus means you can get the value is 1. If the operator is multiplication means you can get the value is 0. Okay, this is the rule of complement. Okay, complement means we are going to change the operator. And this next one, distributive property. So distributive property, here you can see a plus b dot c. Okay, how we can make this expression? Yes, a plus b, right? First expression. Next dot a dot c, a plus c. Okay, this is your second expression by using of this distributive law. Okay, so we given some expressions, we are going to expand this expression. Okay, and next step by step procedure, how we did this or how we can do this expressions in mathematical function. Okay, so first expression is x plus y dash, then x dash dot y. Okay, so now we are going to expanding this form by using of this Boolean identities. Okay, so Boolean identities, here you can see x plus y dash equal to x plus y dot x dash y dash. Okay, so this is your Boolean identity. What is the formula? X plus y dash equal to x plus y dot x dash plus y dash. Okay, so now I'm going to apply the De Morgan's transformations. Okay, so De Morgan's laws I'm going to apply. First one is complement rule, another one is distributive property. So I'm going to apply this true rule in this expression. Okay, here you can get that answer. So how we can get first transformation is I'm going to multiply this value. Okay, here you can see x. Okay, so x plus y dot x dash, you can take this x plus y dot x dash plus y dash. Okay, now I'm going to multiply this one, x into x dash, another x into y dash. Okay, next y into x dash, another y into y dash. Okay, so first expression you can get this one, right? X dot x dash, second x dot y dash, next y dot x dash, and the last one is y dot y dash. Fine. So I'm going to give this value already distribute complement rule. What we have seen, yes, if the value is x dot x dash, you can give the value 0. Whether if the x and x dash, the operator should be the plus symbol, you can get the value 1. So now you are seeing this methodology here. That value is 0. Okay, in your expressions, where can we put this 0? Yes, here you can see. So the first x dash, you can put this value 0, and same y dot y dash. Okay, so both we can put this value 0, right? Remaining what? X dot y dash plus y dot x dash, right? So now we can make this x dot x dash then y dot y dash. Okay, so here you can see so the value is 0 0. So you can get that answer. Remaining x dot y dash plus y dot x dash. Okay. So at last you can get that value x plus y is equal to x dash y dash. Okay, so now I'm going to join this x dash and y dash. Okay, so x plus y and x dash y dash. Okay, here you can get that answer. Here you can see. Okay, x plus y, my expression is right now I got that answer. My expression, the Boolean De Morgan's theorem is true. The condition is true. Okay, so x plus y equal to, I got that same answer, x dash dot. Okay, because they given that operator plus, so I'm going to change that operator multiplication, y dash. Okay, so I got that answer. Okay, so the same answer I got, I proved that Boolean De Morgan's theorem statement also. So the statement is true. Okay, so given the condition is true. So like this we are going to apply in this De Morgan theorem. So it's a very easy methodology and very simple technology which we have implemented in our digital logic circuits. Okay. So here you can see the truth table of that De Morgan theorem. Okay. So x plus y. Okay, finally we got that answer, right? Yes. So the truth table is here. I'm going to pass the input. Okay, already I said we are going to pass two inputs. One is on, another one is off. Okay, so both inputs are off position. You can get that addition. Okay, so if you are using plus operator, you will get that option is answer is 0. Okay, if you are using another expression x plus y, the voltage. Okay, so you can get that input is 0. If you are passing the input is on position, you will get that output is also on position, because that expression should be expanded as x dash y dash. Okay, so x dash plus a plus, okay, a plus a dash. This is your complement law. We can memorize this. A plus a dash, we can get the value 1. Same, similar. Next we consider a dot a dash. We can get the answer 0. Okay. This is for complement rule. We can apply in the De Morgan theorems. Okay. So here the both inputs are true, you can get that output is true. Next, we are passing this information again. If one of the any input is true, the output is also true. Okay. So next expression form, you can get that if any one of the output is true, the result is 5. Okay, in the Boolean expressions. And next, if any one of the input, you can get that true input, right? Next, here also you will get the one input. If the one input is true in this De Morgan's law, you can get that failure output. Okay. Next, given all the inputs are true. For example, both A and B true. Okay, you will get ordinary expression. Okay, so you will get that expression De Morgan's theorem only one A. For example, only one condition is true, otherwise next condition is true. Not both conditions you are going to join. Okay, so De Morgan's theorem what says? A is true or B is true. Okay, but we do not connect with them. Okay, so that is the statement of this De Morgan's theorem. So here you can see this truth table. Okay, so truth table means the De Morgan's theorem says only A is true or B is true, not A and B both are true. So that condition is not satisfied in this De Morgan's theorem. De Morgan's theorem you can prove only one condition. Both conditions you can prove, but we will take only one. Okay, A is true, otherwise B is true. For example, X is true or Y is true, but we should not take both X and Y. Okay, so that condition we have satisfied in this De Morgan's logic circuits. Okay, so next session we can see. Thanks so much for joining.